Welcome to qnawire.
So a portion of this rectangular loop of wire, which has the following dimensions, a length of 0.35 meters and a width of 0.75 meters, is immersed in a magnetic field that has a value of 0.65 Tesla. And that orientation is situated such that the magnetic field points into the page as indicated by these x's. The total resistance of the loop is given as 0.28 ohms, and we're calculating the force required to pull the loop from the field, which is to the right. So if we're pulling the loop away from the field, it will take some amount of force to do that at a constant velocity. And we're given that we want to pull it at a velocity of 3.4 meters per second. So the first thing we want to do is calculate what EMF will be induced by the loop moving from left to right. So the loop will be moving with this constant velocity. And this means that the amount of area immersed in the magnetic field will be changing. So the magnetic flux will be changing. And as we know, EMF induced is equal to the rate of change of the magnetic flux per unit time. So since the area itself is changing, the B field strength is not increasing or decreasing, this gives us a value of minus B times dA dt. So now we need to think, how is the rate of area immersed in the magnetic field changing? Well, if it's moving at a velocity v, then the amount that it moves within a little bit of time will just be v times t, where that's this length, times L, the length of the wire. So for some little amount of time, we can write this as negative b times the velocity with a negative sign, because less area will be covered by the magnetic field at a later time, times the length of the wire. So now we can calculate the current that will be induced in the loop due to the changing flux. And this is simply given by the induced EMF over the resistance. And because our magnetic field is situated into the page, and the amount of magnetic field immersed in the loop is decreasing over time, by the right-hand rule, we know that a current must be generated in the loop in a clockwise direction. So that means at this point, the current will be flowing upward on the portion of the loop that is immersed in the magnetic field. So with a current flowing through this part of the wire, there'll be a magnetic force induced due to the external magnetic field. And this has a strength of I, the current, times L, the length of this rod, times B, the strength of the magnetic field. We know I in terms of the EMF induced and the resistance, and we know the EMF induced in terms of the magnetic field, the velocity, and the length. So plugging in these different expressions, we find that this is equal to the EMF induced over R, because that's our value for the current, times L times B. But because the EMF induced is given by BVL, positive BVL that is, because the two minus signs cancel, this, when fully simplified, will become B squared L squared times the velocity over the resistance. Now we simply have to plug in the values given to find this. This works out to be 0.628 newtons. So this is the force required for us to pull the loop at a constant velocity, given the fact that the magnetic force on this portion of the wire would be attempting to slow it down. So that's our final answer.